So kind of you, so kind of all of you. So let me start with a counting problem in geometry, a very simple problem. And then I'll introduce this fascinating subject of graph theory to you in that. So this is called the Moore's problem. Okay, and it's a very nice way to introduce graph theory. So here I have a circle, right? So if I put 1 point on the circle and look at the number of regions that are formed, so 1 point, so I get 1 region. If I put 2 points, let's say, and I connect them, right, then I get 2 regions, right? So 2 points give me 2 regions, right? Now let me put a third point, right, and make all possible connections. So I connect it to the previous 2, right? So how many regions do I have? 4. So I get 1, 2, 4, okay? And what happens if I put the next one? Can you guess?
It also gets connected?
Yeah, so I connect it to all of them. How many regions? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 4 points, I get 8 regions. Right, so how about 5 points?
16.
16, okay. So let's check it out. 1, 2, 3, 4, 5, and let's see. Okay. All right, and let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So 6 points.
31.
Okay. Yeah, so you guys know the punchline. So yeah, you know, that's the problem with giving lectures to knowledgeable people. Never do that. Okay. So let me try this. I was hoping these circles would be bigger. 1, 2, 3, 4, 5. Okay, so I need one more. 6. All right, so 1, 2, 3, 4, 5. Okay, and this gets connected. Okay, this is, okay, and whoops, I have no idea how am I going to count these, okay? All right. Okay, so shall I draw a bigger circle? Let me do it with a bigger circle because this, I want the, at least the younger people to, there's something missing here. Oh, yeah. So let me do it with a bigger circle. Yeah, that's better. And how do I do this? Typically, okay. 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 Goes there. Goes there. Okay. So now we have to count. So that's 1, 2. Or one line I'm missing? Oh yeah, I'm going to mess it all up. Okay, good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. So you don't get 32, right? So that's the surprise. That 6, sort of the pattern breaks. Okay, so it was like 1, 2, 4, 8, 16, and all of a sudden there's, whoops, 31, right? So we already learned something from here. One is that I always tell people that there's this quote of Russell says that do not be absolutely sure of anything. Okay, and there's only one exception to this. Okay, if you have a mathematical proof, then you can be sure of those things, right? So that's the only exception. And what's a mathematical proof? So you try to observe patterns. So in this problem, there was a pattern emerging, right? Somehow it broke down, right? So a proof is a reason why the pattern will persist, okay, if you find the correct pattern, right? Those are some kinds of proofs. So when I prove something for you, then you can be sure that that pattern persists, that formula is correct, all right? So the Morse problem is, well, what about n points? If you put n points, how many regions? Regions. Okay. So, if it can be captured in a formula, give us that formula. All right. So now we are going to solve this problem using graph theory. There are other ways of solving it, and this is probably not the most straightforward way of doing it, but we'll learn a lot in that way, right? So let's ask ourselves, what's a graph? Okay, so we are looking at graph theory, and of course it will be the study of something called graphs. Now there are these graphs that you study in metric and 10th grade, y equals x squared, right? Graphs like that, you have graphs of functions. That's not what we're talking about. These graphs, I don't know, they seem to have the same name. Okay, these are very simple objects, much simpler than these things. So a graph, if you have a graph, you have to tell me two things about it, and you have given me the graph. One is you're going to give me a set, which we are going to call vertices. Okay, so any set, 5 things, 7 things, it could be children, it could be people, it could be names of cities, all right? And the second thing is called edges. Okay, where E is a set of pairs of vertices. Okay, right? So you will give me, this pair, that pair, this pair, a bunch of pairs. You could give me all of them. You could give me none of them, okay? All right, so you can get different graphs. So one nice way of representing graphs is, for every vertex, you just put a dot, okay, or, something like that. So here's a graph. I'm giving it to you. So in this case, there are 4 vertices. If you want, we can give them names, A, B, C, D. And when there is an edge, you just connect those 2 vertices, right? So here's a graph, okay? In this case, if I want to write it in this notation, which is the set theoretic notation, I'll just tell you the vertices, okay? And then I'll tell you edges, and each edge is a pair. So A is B, A, C, B, D, and C, D. Okay. All right? So actually, the graph is an abstract object. It's a graph theoretic object. This is a picture of the graph. And you could draw it differently. So for example, I could have drawn it like this. This is A, this is C, and this is B, and that's D. Okay, and this picture looks different. Right? So pictures of graphs are different from graphs. This is a set theoretic object. All right, this is a representation of it, a visual representation of it. And you know, if I tell you to draw this graph, two people may draw it very differently. Okay, so that's something very important. Okay, all right. So there was. Here is the first theorem of graph theory. So let's take a graph, and now I'm not going to write down it as a set and things like that. I'll just draw pictures. Okay, so let's draw a graph, and I don't know. Let's make it a bit more complicated. Yeah, that's good enough. Okay, so here's the graph. And this theorem is called the handshaking lemma. All right? Okay, so before I tell you the handshaking lemma, I have to introduce a concept. So if you look at this vertex, there are 1, 2, 3, 4 edges coming out of it. So that's called the degree of this vertex. Okay, so this vertex is V, so its degree in this case is 1, 2, 3, 4. All right? And so the degree of this is 2 edges coming out. The degree of this is also 4, this is 2. It's very unfortunate that I only have 4s and 2s here. You know, you could have other degrees also. Okay? All right. And the handshaking lemma says that the sum of the degrees if I add up the degrees, what I will get is twice the number of edges. Okay? All right? So let's look at a proof of this. The proof is very simple and easy. So what I'm going to do is I'll go to each vertex and it'll have some degree. I'll put an orange arc on that edge. So here I put 2, here I put 2, here I put 4, here I put 4, here I put 4, here I put, and like that. Okay? So how many orange arcs did I put? Well, that's the sum of the degrees. Each vertex, I went around it. There were 7 edges coming out. I put 7 arcs. Then I went to the next and I did that. So sum of the degrees. That's the number of orange arcs. But now let's zoom out and look at every edge. Okay? Between any two vertices. How many orange arcs are there? 2. One came from this side and one came from that side. Okay, so the number of orange arcs is twice the number of edges, and it is also equal to the sum of the degrees. Okay, so that's the handshaking lemma. There's a very nice way of thinking about it. Let's say, some of us came over here and we shook hands, right? And let's say somebody is standing outside and they ask, how many hands did you shake in the room, right? And they add it up. What they will report is 2 times the total number of hands shaken, because each handshake is reported by 2 people, the 2 people involved in it, right? So that's a nice little thing. Okay, so maybe I should give an exercise. Okay, right? And you can just listen to it. Prove that in a graph, the number of odd degree vertices must always be even. Okay, so you can have no odd degree vertices, 2 odd degree vertices, 18 odd degree vertices, but you cannot have 7 odd degree vertices. All right, so that's a neat little thing, you can do it in a little while. Okay, all right, so now I'm going to talk about a really great guy. His name was Euler. Okay, and Some people say that he started graph theory with something called the Coinsberg bridge problem, but I think it existed much before that, right? But he did major contributions to it. So he studied something called plane graphs. Okay, all right. And so these are graphs which have a very nice property that they are drawn in the plane, which means on a board, okay, or on a notebook or something, but edges never cross. Okay, so there are no crossing edges, right? So we're not really talking about a graph, we're talking about a particular drawing also. That the drawing is such that, edges don't cross. Okay, all right? And this, such a graph which is already drawn is called a plane graph, all right? And when you look at this graph, you have not only vertices and edges, but you have another third concept, which is of a region. Okay, because edges are not crossing, you can start with the vertex and you have this thing which is a region. So this is 1, 2, 3, 4, 5, 6, 7, 8 regions, okay? But mathematicians are very strange. Okay, they count the outer region also. Okay, so they'll say there are 9 regions here, right? So, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 regions. So we have vertices, okay, we have edges, and we have regions or faces. Okay, they're sometimes called faces, right? And so Euler, one day he discovered that if you take the number of vertices and you subtract the number of edges and you add the number of faces, you always get the same number. Okay, and that's 2. Okay, and by the way, this is for connected graph, just to be very precise. If the graph is not connected, it's not true, but that's a minor detail. We can ignore it for now, okay? So even if I, have a more complicated planar graph, okay, the number of vertices minus the number of edges plus the number of faces will always remain true, okay? So let's call this thing the Euler quantity. Okay, all right. So to prove this, I need a tool, and this is what I need. Okay, so what he did was he went to his graph and he said, okay, let me erase this edge, all right, and see what I did. I removed an edge, okay, and I merged 2 faces, all right. So my new graph has the same number of vertices. Okay, the number of edges went down by 1, okay, and the number of faces also went down by 1, okay. Since these two have opposite signs, that cancels, and so the Euler quantity remains undisturbed, okay, all right. So what I have done is I've simplified my problem. So I can, instead of studying the Euler quantity of the original graph, I can now study it for this graph. Hey, but then I can repeat this again. Doesn't change. Okay, it doesn't change. It doesn't change. Okay, all right. Now let me stop here. Well, sometimes I run into problems like this. Okay, now if I remove this, I don't merge 2 faces because this is, okay. In this case, he does something different. What he says is, let me get rid of the vertex and the edge. All right. So now the vertices went down by 1, the edges went down by 1, but the number of faces remain the same. Since vertices and edges have opposite signs, the quantity remains the same. So I can keep studying it. So, hey, this is fun. Let's just keep doing this. All right. Okay. Isn't this fun? Right? The quantity doesn't change, 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 doesn't change. Let's stop here. Problem solved. Trivial, right? V is equal to 1, E is equal to 0, and F is the outer face, which is 1. Okay, so isn't that lovely? You know, you start with a complicated thing, you just keep simplifying it, the invariant doesn't change, and so finally the problem becomes trivial. Formally, you'll do this by induction or something like that. Yeah?
Does it have anything to do with 2 dimensions? Like, in this case, we have a planar graph in 2 dimensions. So, if we have a 3-dimensional graph, for example, then what will be the quantity for that?
Okay, so, all right, if you want to embed graphs in 3 dimensions in R3, that's a very boring question because all graphs can be embedded in R3. Okay, so that's not an interesting, that interesting of a problem. There's something called hypergraphs where the problem becomes meaningful. And you know, there are many generalizations of this. This Euler characteristic sometimes is called. This has a lot of applications in topology also. So there are many things. We'll talk about that. We'll come to that 3-dimensional question. Huh? Yeah, Gauss-Bonnet theorem. Yeah, yeah. That's okay. So all right. Now, okay. So now I think we have enough. Oh, I keep losing the eraser. Now I think I have enough to solve the Morse problem. Okay. All right. So.
Morse the same as Morse and Feshbach Morse?
Actually, I very recently found out it was called the Morse problem. So I have done nothing.
Not the Morse code one either.
I have no idea. I'll double check on that. You know, previously Sadia had asked me a question about Karatsuba and I gave you a completely wrong answer. But we did put on the Facebook page the explanation for that. Apparently he had a glorious mathematical career. But it was just he's doing things which I don't understand. Okay. Okay. So here is the Morse problem. So remember here we had n points, okay, on the plane, and then we were connecting them. All right. Let me just not be lazy and do all of this. Okay. Right? So one of the things you might be thinking is, well, this graph is not planar. You know, so what does Euler have to do with this? Right? But there's a very nice way to, if you have already drawn a graph to make it planar, what you do is you go to every crossing and you add a little vertex there. Okay, so you add these purple vertices. Okay. I think there are edges missing, so that's why there are purple vertices missing. Okay, just keep telling me, this vertex, no?
Yes.
Okay, yeah. Good. Okay, so you add these purple vertices. Okay, all right. So now we get a graph. Actually, we have a multi-graph because these things are connected twice. Okay, but you could remove them and adjust for that. If you don't, things still work out. You know, the theorems that I've written happen to be true for this graph also. So we can go ahead. All right. Otherwise, if you feel nervous, you can just remove them and work out the adjustments that happen. All right, okay, so this graph has the original white vertices, okay, and then it has these newly created purple vertices. So if we can count the number of vertices and we can count the number of edges, right, then we would be fine because we have the Euler formula and then we can work out the number of faces. All right, so in this, the number of vertices originally was n, right? Those were the white ones. So now the question is how many purple vertices are there? Okay? All right. And here's the observation. if you look at a purple vertex, when you go in this direction, you get to a pair. And when you go in this direction, you get to a pair. So each purple vertex corresponds to 4 white vertices. All right? So in other words, if you have 4 white vertices and you connect them, okay, you get a unique crossing. Okay? And if you have a crossing that takes you to 4 unique white vertices. Okay? So the number of purple vertices, it should be equal to the number of, so you have a pair and then in what you have a quadruples, right? Sets of size 4 of white vertices. Okay, all right. Okay, so how many ways can I choose 4 white vertices out of n, right? Now, you know, this thing is taught in metric and things like that, but most people don't know it, but mathematicians have a name for that quantity. It's called n choose 4. Okay, which is how many ways you can choose n things out of 4, n choose 4, right? They used to call it what, NC4 or something like that in notation, which I never understood, but you know, the standard thing is just write n choose 4, you know, okay?
It's called binomial N4.
Yeah. Yeah, so
In mathematical, that's how you'd represent it.
oh, yes, yeah. Okay, so so that's the number of vertices we have. All right, let's count the number of edges. Well, to count the number of edges, we have a nice trick, the handshaking lemma. Okay, so each white vertex has n plus 1 things coming out of it because of these 2 extra. You know, it's connected to all of them, which is n minus 1 plus 1 plus 1. Okay, so there are n vertices, each having degree n plus 1. Okay, this is, I'm summing up the degrees, then I'll divide it by 2. Plus, what about the purple vertices? They all have degree 4. Right? So it's 4 times n choose 2. But remember, sum of the degrees is twice the number of edges. So I have to divide this by 2. So I get over 2 here. And this becomes a 2. Okay? Now my Moore's problem is almost done. Okay. Oops. Right. So V minus E plus R is equal to 2. But remember, in the original problem, Morse was not looking at the outer area. You know, outer face he wasn't counting. So, you know, this is off by 1, so we have to correct it. So this becomes 1. Okay, yeah, I've been calling this F, right? So F is just going to turn out to be E minus V plus 1, and this is 2 n choose, oh wait, this is a 4. 4 plus n times n plus 1 over 2 and minus the number of vertices, which is minus n choose 4. So this, and there's a plus 1, which I've copied from here. Okay, so this cancels, and this is n choose 4, and if you do a little bit of algebra, this is n times n minus 1 over 2 plus 1, and you can nicely write it as n choose 4 plus n choose 2 plus n choose 0. Okay, so that's the answer to Moore's problem, right? So it's a quadratic polynomial. Okay, many people, you know, who have a bit of experience, when you show them the Moore's problem, they know that the exponential growth can't be sustained. It has to be a power law, so they become skeptical, right? But it's a nice way to try to trick, you know, high school students or young people into it because there's so much to learn, right? So that's the end of the Moore's problem. Okay, all right. So now let me do something else. Okay. Okay, so I'm going to talk about another handshaking lemma. Okay. And this time, again, we are going to look at a plane graph where edges don't cross. So I'm not going to make it too complicated. Just this one is good enough. Okay, so here we have 1, 2, 3, 4, and 5 face, the outer face. All right, and each face has number of sides.
Now, let's see, when you take the large n limit of that, what do you get? You get n to the power 4.
Yeah.
Huh?
Constant times n to the power
Yeah.
4. Yeah.
Goes as n to the 4.
Yeah.
So do you know the next number in the sequence after 31? What comes after 31?
It's 7 choose 4 plus 7 choose 2 plus 1. I think it's 47, I'm not sure. Okay, so here is a graph, and you have 1, 2, 3, 4, 5 faces. This face has 5 sides. Okay, so there's 5 sides. This has 4 sides, this has 3 sides, this has 4 sides, this has 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. Okay?
That has 3 sides or 4 sides, the bottom triangle?
It has 3 sides. Okay, yeah, all right. And now the second handshaking lemma says is that the sum of the sides of the faces is equal to twice the number of edges. Okay, all right. And actually, I mean, if I were teaching this as a class, I'd probably ask students to do this themselves because the proof is very similar, right? But since there's not a class, so I'll do it for you. What I'm going to do is
What does this mean, sum of the sides of the faces?
So this is a face with 5 sides. Okay, so I take 5 plus 4. There's 4 sides. This has 3 sides. This has 3 sides. Okay, and the last one has 9 sides. And the thing is, I'll get twice the number of edges. Okay, and the proof is the proof will clarify what I'm trying to say. Okay, so this has 5 sides. So let me go and put a dot on every side. Okay, so how many dots did I put? 5. And here I'm going to put 4 dots. And here I'm going to put 3 dots. And here I'm going to put 3 dots. And for the outer one, that's why they have the outer guy, to make life nicer. I'm going to put, I don't know, 9, whatever number of. Okay? And now zoom out and look at an edge. Okay? It got 2 dots, one from one face and other from the other face. All right? So that's a nice little theorem. Okay? All right. And now we can do something interesting. Okay, so sum of the sides of the faces is equal to twice the number of edges. That's what we have. Okay, but when you make a face in an ordinary graph, all right, what's the smallest number of sides it can have? 3, right? It cannot have less than 3 sides. 2 sides don't make a face. Okay? All right? So the sum of the sides of the faces must be greater than or equal to 3 times the number of faces. Okay, each face gives me 3, sometimes it gives me more. Okay, so the quantity I will get will be greater than 3 times the number of faces. So for example here, let's try this example. This gave me a 3, this gave me a 4, this gave me a 3, this gave me 1, 2, 3, 4, 5, 6. Right? So each one of them gave me at least a 3, and this has 1, 2, 3, 4 faces, so the sum of the sides of the faces must be greater than or equal to 3 times 4. You know, each face gives me at least 3 sides. All right? So now I have 3f is less than or equal to 2e, and I have v minus e plus f is equal to 2. Right? So I have 2 equations. No, I don't have 2 equations. Sorry. I have 1 equation and 1 inequality. I should be able to get an inequality and remove 1 variable. Okay, so I'm going to try to get rid of this f. Okay. All right, and let me do that here. Okay, so let's multiply this with 3. So you get 3v minus 3e plus 3f is equal to 6. All right, and then we have 3f is less than or equal to 2e. So I have an inequality, there's an imbalance. If I subtract equal things from both sides, I get the same imbalance, right? You know, if you remove same quantity from both sides. So when I remove this, this f cancels, and I get 3e minus 3v, okay, and this is less than or equal to 2e minus 6. Okay, now 2e I take there, it cancels, so I get an e here, and this is less than or equal to 3v minus 6. Okay, right? This is beautiful. Okay, let me write down what I have concluded. Okay, and now I'm going to use another term. Planar graph. Okay, the number of edges must be less than or equal to 3 times the number of vertices minus 6. Right? And what is this planar graph? Previously, we were looking at graphs which are already drawn on the plane. All right? But planar graph is one that can be drawn on a plane. So if a graph can be drawn on a plane, it must satisfy this quantity. Okay? Because if it can be drawn on the plane, then, you know, all those things were true, and, you know, my whole logic goes through, and I can conclude this. Right? Okay, so here's a lovely thing. Let's look at this graph. Okay. Okay, this has a name, it's called K5, because there are 5 vertices, everybody is connected to everybody. So the number of vertices is 5. The number of edges is actually 10. You could count that. Or you could just say every vertex has degree 4, sum of degrees is 20, so the number of edges would be that. So what we do is we look at 3v minus 6, and that turns out to be 9. Okay? So E is not less than or equal to 10 is not less than or equal to 9. So this violates this inequality. That means no matter how hard you try, you can never draw this graph without an edge crossing. Okay, so this graph is inherently non-planar. Okay, so this K5 is inherently non-planar. It's not a bad drawing. Well, this one is a bad drawing because it has 5 crossings. You know, you could probably do with less, but they will always be, huh?
That one on the left, that's the simplest, I guess.
Non-planar?
Non-planar.
No, why is this non-planar?
Crossing OD.
Oh, you're saying K4. ये जो आप K4 कह रहे हैं ना, look, this is, you're saying this is a K4. This is not a non-planar graph. This is a bad drawing. Let me redraw it again for you. Okay? I go like this, I connect these two like that. Okay? If you don't like that drawing, I can do another one for you. That's also K4, no crossings. Okay?
But in
Right.
K5, if you define these as vertices where the crossing is happening,
Yeah. Well, but then you change the graph. Yeah, then you have changed the graph. Okay? All right? Okay. All right. Okay. Now let me, okay, and I'm going to give an exercise also. There's another graph which is this graph. Yeah. Okay, this is called K33. Okay, there are 3 vertices upstairs, 3 vertices downstairs. Everybody hates their own group and likes everybody else in the other group. Okay, so this is called K33. Now, here's a thing about this graph. The number of vertices is 6, right? The number of edges you can count is 9, and you can do it, all right? And E is actually, well, let's do 3V minus 6. So that's 6 to 12, all right? So 9 happens to be less than or equal to 12, okay? What does that mean? Absolutely no. Look, all right, remember that we have said that if a graph is planar, then this condition must hold. Converse we have not proved. And that's the biggest mistake that students, people on TV, everybody makes. You know, you know that they prove one side and they try to use the converse. The converse is not necessarily true. All right. In this case, you can prove this graph is not planar, right? And remember, we had 2 inequalities. One was V minus E plus F equals 2, and other was 3F is less than or equal to 2E. And we put them together and we got this inequality, right? At one point, we argued that every face must have 3 sides to it, right? That's why the 3 came from, right? In this graph, you cannot have a face with 3 sides, okay? It has to have 4 sides because this graph doesn't have a triangle, okay? So the argument can be improved. This inequality can be improved. All right? So for triangle-free graphs, you have a better inequality. And that will help you prove that K33 is non-planar also. Okay? All right? So that's why knowing proofs is very important and knowing each place where we argued something. So, you know, we said every graph, I mean, smallest face can be a triangle, but if the graph has no triangles, then the smallest face has to have at least 4 sides, and you can improve the argument. Okay? So I will not do the details of that. I'll leave that as a homework reading. But I want to tell you now one very lovely theorem. Okay? And I will not prove that. I'll just tell you about it. So here's K33, our favorite, and then here's K5. Okay? Okay, all right. Now suppose if I start adding stuff to this graph, you know, will this graph be planar? And the answer is no, because it has a structure which is not planar. If you could draw the whole thing without edge crossings, you could remove this stuff and get a drawing of K5. Okay, so if K5 is somewhere in a graph, you know, you can never hope for it to be planar. Same is with K33. Another thing is that what if I go and add edges? So this thing is called subdivision. What if I go and add vertices along an edge? Okay, is it possible for this whole graph to be planar? The answer is no. Because if it were, you could just remove them and you'll get a drawing of this K3, which you know is not planar. The converse is also true. Okay, a graph is planar if and only if it doesn't have a subdivision of K5 or K33. So there are two fundamental objections to planarity, the ones in front of you. There aren't any other objections to planarity.
All others can be like disentangled
Into a planar drawing, yeah.
all others.
Yeah.
Any kind of graph.
Yeah, it's an if and only if. So these are the only two objections to planarity. Yeah, this is called Kartowski's theorem. And it can be proved in a graph theory class. Maybe one lecture, maybe 1.5 lecture. It's
Like the prime numbers of planar graphs
yeah, the objections, yeah.
and be subdivided into simpler.
Yeah. Okay. All right. So are you guys having fun or is it getting too long? Okay. All right. Okay. So let's do something else. One more thing I'm going to do and then we can. So can you show us that वो एक आपको चीज़ दिखानी थी क्योंकि मेरी drawing 2 dimensions में इतनी ख़राब है तो I don't dare do anything with 3 dimensions. Okay, so these are solids, these are called Platonic solids, okay? And we will talk about them a little bit. But इनकी property ये है कि ये जो solid है अगर आप इस vertex को देखें तो यहाँ पे 3 edge यहाँ मिलते हैं 3 edge यहाँ मिलते हैं 3 edge यहाँ मिलते हैं 3 edge यहाँ मिलते हैं. So every vertex has the same degree, right? And अगर आप एक face को देखें तो उसके 3 sides हैं तो सारे faces के 3 sides हैं. So they have this property. The vertices are in some sense identical to each other and all the faces are identical. This is a cube. यहाँ पे 3 मिल रहे हैं 3 मिल रहे हैं हर face square है. This is called octahedron. इसका हर face triangle है और यहाँ पे 4 मिल रहे हैं. और ये जो है इसका हर face pentagon है और यहाँ पे 3 मिल रहे हैं. इसका हर face triangle है और यहाँ पे 5 मिल रहे हैं. Okay, that these are 5 solids that were known to Greeks that they are Platonic. These are the only ones. I have no idea how they knew that these are the only ones, but I've read it in maths history books that they knew, but I've never really dug into it. There must be a reason. Okay, acha. Now what you can do is you can imagine like putting a balloon in there, and and then what happens is if you put the edges and the vertices, they won't cross. Right? Because that's how the thing is, right? You put a balloon inside it and you'll get a graph in which there will be no edge crossings for all of them, right? That's what we want to observe. So the question is, why are there 5 solids only? Okay, is there a reason for it, or one has to think about a proof. So let's do that using graph theory.
इसका कार्ल सेगन की जो बुक है ना कॉस्मोस उसमें भी इसका बड़ा अच्छा प्रूफ है अपेंडिक्स में मैंने बहुत पहले पढ़ा था तो वो उसमें मतलब ही इज मतलब एक्सप्लेनिंग ऑल सॉर्ट्स ऑफ थिंग्स इन दैट बुक so he mentions the Greeks as well so he gives a proof of why only 5 platonic solids are possible in the appendix मुझे भूल गया लेकिन बड़ा beautiful proof था वो
let's
बहुत
see
simple था वो
let's see if this one is the same or similar. Yeah. Okay, so the thing is that if you take a Platonic solid, okay, then it gives you a planar graph, okay, which has, each vertex has same degree, Remember, each vertex, the number of edges coming is the same. So let's call it A, all right? Okay, so each vertex has to have, A things coming out of it or coming into it, however you want. And each face is identical, All right, so each face has B sides, let's say. Okay, so here's your face, and so it has B sides, right? And not only that, they have to be identical, and we're not going to worry too much about that, right? So you get a planar graph, all right, and what do we know? That the sum of the degrees is twice the number of edges. So 2 times the number of edges is the sum of the degrees. So there are V vertices. So the sum of the degrees is AV. And from here, you get that the edges must be AV over 2. Right? That's our first conclusion. All right. But remember that the sum of the degrees is also sum of the sides of the faces is also twice the number of edges. So this is B times F, all right? But twice the number of edges is AV, so this tells me that F is equal to AV over B. Okay? Yeah, so this is the information I have. And now I go to my Euler formula, which is sometimes called the second most beautiful formula in mathematics. V minus E plus F is equal to 2. So this is V. This is AV over 2. This is AV over B. And this is that. All right? So let's be clever. If you do your homework and divide by AV. Okay, so if I divide this by AV, I get 1 over A minus a half plus 1 over B, okay, is equal to 2 over AV. And let me just do, one small thing. This tells me that 1 over A plus 1 over B has to be equal to half plus 2 over AV. This quantity, however small, must be greater than 0, right? So this is strictly greater than half. Okay? All right. What else do we know about A and B? Okay. So A and B are both greater than 3, right? A face has at least 3 sides, and a vertex has at least 3 things coming to it, So it's that. And we have that AB are integers. Okay? So let's see. If I take A equals 3, right, can B be equal to 3? Right? 1/3 plus 1/3 is greater than 1/2. It's 2/3. So yeah, it's a possibility. Can B be equal to 4? 1/3 plus 1/4 turns out to be it's greater than a half. So that's a possibility. Can B be equal to 5? Okay, 1/3 plus 1/5. Yeah, and that's fine also. All right. Can B be equal to 6? Well, 1/3 plus 1/6 is actually equal to half. So you wouldn't exceed a half. So B equals 6 is not possible. 7 is not possible. 8 is not possible. Yeah. Yeah. So these are the only possibilities. Okay. Similarly, what you can do is you can say B is equal to 3. Then the only possibilities are Okay, because otherwise the numbers are too large and they just don't satisfy this inequality, right? So in this 3, 3 is a common one. So there are actually only 5 possible pairs. There are 3, 3, 3, 4, 3, 5, and 4, 3, and 5, 4. Okay, these are the 5 right? This is a tetrahedron, okay? That's a cube, that's an octahedron, and this is the icosahedron, that's the dodecahedron. The rest you can, just figure out.
You can get to the Platonic solids also by considering the rotation group, looking at the representations of the rotation group and using Young's tableau to figure out the dimensionality of those representations. But that's a longer, more complicated route. This is nice and simple.
Yeah.
But they all meet at the same point.
Yeah.
Handshaking also had the same proof. I remembered it now.
Huh?
Handshaking also used the same kind
Similar,
to eliminate possibilities.
Yeah. So it's amazing.
Very simple, profound conclusion.
Yeah. So let me there was one more thing I wanted to talk about, but if I realize that if I talk about it, it'll take too long. So I'll tell you a little bit about it, and then we'll stop and have questions. So people were interested in one problem. So remember when we made these planar graphs, right? You can think about maps, maps of countries. And what you want to do is then you want to color these maps, like India and Pakistan can't have the same color, that'll be, or something like that. Neighboring countries should not have the same color because that'll be confusing. And so people wanted to color maps, and the question was, given a planar map, which is a regular map that you get, what's the minimum number of colors you need so that neighboring countries which share a border always have a different color, all right? And you can talk about maps, but what you can do is you can put a vertex inside each country and then connect them, and that's called the dual graph. So you're actually coloring vertices now, okay, rather than coloring faces. It becomes conceptually easier. Also, you can talk about coloring non-planar graphs also if you just color vertices. And one of the conjectures was that for every map, 4 colors suffice, okay? And, it was a problem for 100 years. It was 1870s. The problem was posed that 4 colors suffice. And it's pretty fascinating history that there was a proof given by Kemp which stood for decade till people realized it was wrong. And then there was a streak of wrong proofs, which stood which were accepted for decades, 2 or 3 times, till eventually people will find something was wrong with it. And at one point it was, never as famous as Fermat's last theorem, but it was one of the problems that you could easily pose to high school students, undergrads, and all that. And finally, it took about 100 years to come up with the correct proof, and the 2 mathematicians who did it were from University of Illinois, Appel and Harten, in the 1970s. And when they proved it, okay, the University of Illinois Maths department had a special stamp made which said 4 colors suffice. And every envelope that will come out of that maths department was stamped 4 colors suffice. Okay? And it was the first major proof of Appel and Harten that used computers. So in some sense they argued that here is an algorithm and it generates these graphs. If all of them can be 4-colored, then the 4-color theorem is true. But the number of cases was in thousands, so computers had to be used to check that that their proof was correct. At that time, it was 1977 or something. It caused a huge controversy. Many mathematicians refused to accept the proof, but it seems like it stood the test of time, and now it's accepted. So graph theory is a very vibrant field, and there are many areas that it can be used in. Especially in computer science, you can imagine like airlines, cities, and social networks. They all model with graphs. So let's stop here, and I'll take questions.
Sir, Sir, can you give examples of any like practical applications in networks, a theory of networks, or in, for example, like security and so on, where these ideas were applied, a game theory or economics or something?
Oh, well, game theory, there's a deep connection, okay? But if you're talking about computer networks, I mean, just imagine each computer is going to be a vertex, right, with a name. And, if it's connected to another computer, you put an edge, okay? So it may have a direction, all right? So graphs have a lot of cousins, like directed graphs or weighted graphs or things like that. So you model these problems with. So, for example, just think of Google Maps, right? There's an underlying graph, right, which is taking you where each possible place where you get off is a vertex, right? And then, there's an edge, which is the road, right? But that edge has a lot of information. It's not just an edge, but it's an edge with a database behind it, right? How wide is it? How long does it take? And all that. Right, so everywhere, yeah.
Let me give an example, and that comes from quantum field theory, quantum chromodynamics actually, where you can draw any number of graphs. Now, it turned out that Gerard 't Hooft, who later got the Nobel Prize for something else, established a very important theorem. He said those graphs which are planar dominate in the limit where the number of quark colors goes to infinity. And so this is the one particular case where quantum chromodynamics can be actually solved.
Oh.
And after he proved that theorem, there were hundreds, I'd say 1,000 papers, which then went into the solution of quantum chromodynamics. And so that's the most important application that I can ever think that I know of.
Yeah. So, Google Maps, I would say, currently is also something we all use. So.
I have a question. What defines a region or a face? From what I understand, it's that it should be enclosed by the edges.
Yeah.
But then how can you define the outside as a region? I mean, one could if one imagines that it's somehow three-dimensional and
No. Here's the thing. Actually, we're not looking at planar graphs. We are really drawing the graphs on a sphere. Okay. So
Yeah,
then
it's
the
clear.
outer region is not an outer
Yeah.
region.
Okay.
It turns out that every planar graph can be drawn on a sphere that you can easily see. You just paste it somewhere. And every graph drawn on a sphere can be made planar by stereographic projection. So the interesting question that you were talking about is what graphs can be drawn on a torus? Okay, because think about torus is a sphere with a handle attached. So you can route edges, under and above it. Okay, and it turns out that you can draw a case 7 vertices all connected on a torus. Whereas you can't draw a K5 on a sphere. Yeah.
I just remembered another application, and that is for making an implosion atomic bomb. So in a bomb, what you have is an outer layer of explosives, and they all have to be triggered at the same time, and then they have to come towards the core, which then compresses, and then you have the bomb. So how many surfaces of explosives can you have? That is determined by Euler's theorem.
Does this piece of mathematics has any connection with the AI or the modern technology?
Oh yes, a lot of the graph theory is to AI or computer science what physics is to calculus. If you want a lot of calculus problems, just ask physicists. Almost every question they have, mechanics, you'll get. So in computer science, the way we make students really understand things and get good at it is we give them graph theory questions. They're slightly different in the sense they are supposed to write algorithms, okay, that, there'll be a graph, tell us how to go from this vertex to that vertex in smallest number of steps or at the smallest cost or something like that. These are very used a lot in AI.
Thanks.
Yeah, although AI is not my interest.
That's the future.
It doesn't matter, you can remain classical.
I have a question. W- Okay, so why is the graph theory so important in the scientific community? Can you explain that?
Well, because it is needed in many applications. That's the reason, right? So, for example, if you play video games, right? To do programming for a video game, there's some kind of a graph there somewhere, which is being manipulated and all that. All right. So what you're shown is the outcome, the output. But the technology behind has a lot of mathematics, and there's many kinds of mathematics that are used. There are lots of. So, for example, you have these cartoons and all that, and these 3D things. So a lot of physics is used just to render their hair. So you need that kind of knowledge to do applications. All right. But the other reason why we do things is we find these things fascinating, They have interesting properties, Just like a flower is interesting. So just like that, graphs are interesting.
Thank you.
Since you guys here, I want to take this opportunity to just ask a question, especially Parvez Saab, you sound very expert in mathematics too. Mathematics is a very important subject, and especially recently in UK, they made the law, right? They're going to teach mathematics at every level, right? So, after it's right, I want to just know what's the best way, because my background is actually in finance. I'm not really good at math, but I want to teach mathematics to my kids. So, what do you guys suggest? Like, what's the best way to start teaching them, and how we can build their concepts so that they can be better, they get better at mathematics and like these sort of subjects?
Parvez, you want to? Okay. All right. So I think that one of the best things you can do for your children is to, one of the best ways you learn is from your peers, from your friends. So, if you can get a bunch of children excited about maths problems, and if they can come to places like this, where they meet other children who are interested in science, that's one way to do it. The other is there are a lot of stuff is available now on the YouTube, so and on the internet. The problem is there's so much stuff available that it's hard to sift through it and say which one is right, which one is good, which one is bad. But there are some reputed channels. Typically, I would say find out the person who's presenting it and try to find out their university's affiliation. If he's from a good university, if he's a professor, that's, that means he's actually he's not going to teach. So, lots of resources are now available. Khan Academy is one. If you can train your children to learn from there, that's...
Although you don't have to be from a good university. All that is wrong. कोई ऐसा बंदा मिल जाए जहाँ से भी हो, doesn't matter. As long as you enthuse kids about something, it's fine.
I remembered another application of graph theory, and it was an electrical circuit. So I remember in FSC, I was really confused about how do you set up equations for circuits and how to find these voltages and all that. But then I found this book, and it started. The title was Topology of Electrical Circuits, and it started with an introduction to graph theory and concepts such as trees, and then it built up that formalism and made it at the end of the day, when we're setting up equations for circuits, it made it so algorithmic, like you don't even have to think, and that made me appreciate like how you can set up equations through the notion of graph theory without making some arbitrary choices. Like the underlying notion of the graph makes it just trivial to see what equations are coming out and how to even prove certain theorems, like the conservation of energy in an electrical circuit. All those came out naturally, and that was just amazing application.
That's
Yeah.
That's there are lots of amazing applications. So so a lot of people study graphs without taking a formal course in graph theory because it just pops up in so many fields. Yeah, that's nice.
Kepler also used the Platonic solids to create his model of the solar system, which was very interesting. Because he thought that the distances of the various planets to the sun must have like a precise mathematical relationship, and so he used, and only not all of the planets were known at the time.
Only 5.
So only 5, the traditional ones.
Yeah.
So he was able to embed them in nested Platonic solids, starting from 1 and then becoming more and more complicated, and charting their orbits around their complicated shapes. But that turned out to be completely false.
Yeah.
Very similar to how I guess it was Rutherford or a scientist at the beginning of the 20th century, late 19th century, who used the idea of knots to describe atomic structure, various atoms. Who was he? क्या नाम था उसका? नाम मुझे भूल गया उसका. कोई classical British physicist था, बड़ा famous. तो वो he used the idea of knots because knots were also being classified at the time. So he had the bright idea that maybe atomic structure is based on knots, and the simplest atom, hydrogen, is the unknot, which has no crossings. And then as you go progressively more complicated, you get knots with more and more crossings. He was able to connect the two very, very precisely, but that also turned out to be false. So sometimes beautiful mathematics is applied wrongly.
He was inspired by smoke rings. He used to smoke a pipe a lot. So those knots used to get tangled with each other.
And also, one of his good friends was the mathematician William Tate, who was the preeminent knot theorist of the time, and he was the one who classified. So it was from his friend that he got this idea, because he was a physicist, and he learned all about knots from his friend, so he decided to connect the two.
Yeah.
So it's very interesting history, how these things can be applied sometimes.
Yeah. I mean, physics is a very difficult subject. I feel that. I don't know. Sometimes the problem is it's getting, when you start trying to understand quantum mechanics in these subjects, it gets so bizarre and counterintuitive that I just lose it. I have no intuition for it. So, shall we end here? Yes. Okay. Thank you so much. अच्छा. क्या ऑनलाइन?
चूँकि द ब्लैक होल के फेसबुक पेज पे ये लाइव भी नशर हो रहा है, तो हमारे साथ ऑनलाइन भी कई दोस्त हैं. उनमें से अमाद खान है एक, विद हिज क्वेश्चन ही आस्क्स, हाउ कैन वी एफिशिएंटली फाइंड द शॉर्टेस्ट पाथ बिटवीन टू स्पेसिफिक नोड्स इन अ लार्ज weighted graph with millions of vertices and edges?
Yeah, there's a classical Dijkstra's algorithm, which, it takes at least half an hour, 45 minutes to take an algorithms course. Take a course in graph algorithms. Teachers teach that, hopefully. Dijkstra's algorithm, if you search for it, he'll find many sources.
You can write the name here so that
Dijkstra, if I can spell it. By the way, finding algorithms for shortest paths is harder than buying a car. There's so many options available depending on what you're looking for.
There is another. Mamoon Abdullah है हमारे साथ, वो पूछ रहे हैं, can you please tell some applications of algebraic graph theory in industry.
Algebraic graph theory. Okay, I have no, but algebraic graph theory in the industry, I can tell you one application. So for example, there's something called expander graphs, right? So they have a lot of applications. You can, for example, prove that the social networks are expander graphs, all right? And that allow you to do a lot of searches on them. So that's, but applications is my sort of weak area. Next one.
I would like to respond to more.
Go ahead.
One application of these graphs is in isogeny based cryptography, where we draw these large graphs which are Ramanujan graphs, which are applied in cryptography.
Yeah,
so
expanders have a huge applications in cryptography.
So there's one application over there.
Yeah.
So sir, मैंने इंटरनेट से भी निकाला है, तो you were wondering ना कि how the Greeks discovered these Platonic solids. So Euclid has argued in proposition 18 of book 13 how there can only be 5 Platonic solids. So we can read that. So later on.
Yeah.
So so they did have a proof, and they have written that Pythagoras discovered 3 of the Platonic solids first. Maybe the simplest ones, tetrahedron, cube, and the third one, octahedron probably. And it was later Theaetetus, who was a contemporary of Plato, who discovered the remaining 2. And then Plato mentioned it in his Timaeus, one of his dialogues, that connected it with the earth, fire, air, and water, and so on. So they do have a proof in Euclid of this.
Yeah. So the early mathematicians had this sort of superstition which misled science at times, I feel.
Lots of crystal structures, all crystal structures are based on these Platonic solids, and the fullerene, for example, is a truncated icosahedron structure. The buckyball.